So section 4.5 and 4.6 focuses on solving polynomial equations. With number 1, we'll just jump right into it. It says let f of x equal x plus 2 times x minus 1 times x plus 4. And the first question asks us, what is the degree of f of x and y? So when we've talked about degree in the past in section 4.1, it was pretty much when everything was already in standard form and you're just looking at like what is the highest power on x. But this is like in factored form. So if we were to multiply it out in standard form, you could get like the highest, or you could look at the highest degree of x and it'll tell you the degree. But you don't necessarily have to. If something is in factor form like this, you just kind of have to look at how many x's are being multiplied together. There's 1, 2, 3 x's that would eventually be multiplying together to go into standard form. So that means it's degree 3. So degree 3, because there's 3 x's being multiplied together. If we were to multiply this through, like FOIL it and everything like that, and get it in standard form, it would end up being x cubed and then in the following terms. And then for B, it says find the x-intercepts of f of x. So if we wanted to find the x-intercepts of any function whatsoever, we could kind of set either f of x or y, however it's written, to 0 and solve for x. So if we want to find these x-intercepts, I'm going to replace f of x with 0. So 0 equals x plus 2 times x minus 1 times x plus 4. And because this is already in factored form, I can just set each factor equal to 0 and solve for x. So x plus 2 equals 0, x minus 1 equals 0, and then x plus 4 equals 0. For x plus 2, subtract 2 from both sides, get x equals negative 2. For x minus 1 equals 0, add 1 to both sides, get x equals positive 1. And then for x plus 4 equals 0, subtract 4 from both sides and get x equals negative 4. So x equals negative 2, x equals 1, x equals 4. That means we have x-intercepts at negative 2, 1, and negative 4. Or like negative 2, 0, 1, 0, negative 4, 0. And then if we want to sketch a graph based off those x-intercepts and degrees, this is really enough information to sketch the graph. So we'll draw our x and y axis. And then we'll have to scale our, we'll have to scale our x-axis, but we don't really want to scale our y-axis, at least not yet. So if we have x-intercepts at negative 2, 1, and negative 4, I'm just going to scale it by 1, and then we need to make sure that we go all the way down to negative 4 on the left side. And you can just start by plotting your x-intercepts first, because those are the points that we know for sure. So I know I have an x-intercept at negative 2. I have an x-intercept at positive 1. And then I have an x-intercept at negative 4. And then from there, we kind of have to remember what end behavior we're going to have based on the degree of the polynomial. So since this is a degree 3, it's going to be, our end behavior will finish off going in 2 different directions. So if it's a degree 3 or an odd degree, our graph is either going to have one end going on the left side going down and the right side going up, or it could be vice versa. It could be the opposite of that. So when we're deciding whether the graph is going to be increasing or decreasing overall, we need to look at the lead coefficient. And we can look at the lead coefficient like even in factor form. Like our coefficient out in front of here would just be 1. And if we multiplied this all the way through, it would still be like 1, and 1x cubed would be our first term. So since the lead coefficient is positive, this is what our graph is going to look like, because it'll be increasing overall since it's a positive 1. So from there, we can kind of start to put our graph together. So if our graph is going to finish going up, so as we go to the right, it goes up, That means for my rightmost point, I can go up. And as our graph goes to the left, it finishes down. So for my leftmost point, I can go down. And then from there, we're just going to cross through each intercept. It doesn't really matter how far up and how far down we go because we don't really know like these specific turning points. So I'm just going to come up through that y or x-intercept of -4. At some point, it'll turn back around and go through that x-intercept of -2. And then at some point, it'll turn back around and cross through that x-intercept of 1. So where you're making this turn around, it doesn't really matter because we don't know those specific points right now. So I could have drawn this like going way up here, going way down here, but for right now, we're focusing not mostly, but only on the x-intercepts and the end behavior. So where it finishes when it goes left or right and where it finishes when it goes left. And then for example 2, it says below is, or this should say is the graph of g of x equals x minus 2 squared times x plus 1. So first ask, what are the x-intercepts of g of x? So same thing goes, if I wanted to find the x-intercepts of any function, I would replace, in this case, g of x was 0. And then this is already factored, so I would set each of those factors equal to 0. And you can kind of do this in your head. Like if I set x minus 2 equal to 0, I would get an x-intercept or a solution at x equals 2. And if I were to set x plus 1 equal to 0, I would get a solution at x equals -1. So that means for my x-intercepts, I have an x-intercept at 2, 0 and -1, 0. And you can see those x-intercepts on the graph as well, so it goes both ways. If you're given the graph, like yes, you can look at the graph. If you're given the function, you can just set the function equal to 0 and solve for x. It's up to you. And then for what happens at x equals 2. So we know we have an x-intercept at 2, 0, but if we look at our graph, it bounces off at the x-intercept 2. So like it goes up, it comes back down to 2, and instead of just crossing through it, it bounces up off of it. So for what happens at x equals 2, we could say either the function touches or we could say it bounces off x equals 2. So it bounces off x equals 2. It doesn't cross the x-axis at that point. And then the little note below says, notice x minus 2 is a repeated factor. So that means that x equals 2 is a double root, and the graph touches the x-axis but doesn't cross it at the repeated 0, x equals 2. So a repeated factor or a double root, that comes from the x minus 2 being squared. So because this is x minus 2 squared, we call it a double root, and that just means that the function is going to touch it and not cross through it. And then for number 3, it says given f of x equals 5x cubed minus 40x squared plus 80x, first thing it asks us to do is find the zeros of the function by factoring and using the zero product property. So if we want to find the zeros first, it gives us a note, we need to replace f of x with 0. So 0 equals 5x cubed minus 40x squared plus 80x. So the first thing if I want to factor is to check for greatest common factor, and each of these is divisible by 5, and they both also have at least x to the first power, so I can factor out of 5x. So 0 equals, and then if I factor out of 5x cubed divided by 5x leaves me with x squared, and then negative 40x squared divided by 5x leaves me with negative 8x, and 80x divided by 5x leaves me with 16. So once I factor out the 5x, I'm left with x squared minus 8x plus 16. And then because the coefficient of x squared is 1, I'm just looking for factors of 16 that add up to -8. So it would be -4 and -4. So it would be 0 equals 5x stays out in front. And then it could either be x minus 4 times x minus 4, or we can simplify it by writing it x minus 4 squared, since it's the same number, like the same factor that's multiplying to positive 16, adding to -8. So we have 0 equals 5x times x minus 4 squared. And then if we want to find the zeros, we just need to actually like solve the equation. Basically, that's what finding the zeros means. So I'm going to set each factor equal to 0. I'll do it over here. So 5x equals 0. And then x minus 4 squared equals 0. And then for 5x equals 0, if you divide both sides by 5, you get x equals 0. And then one thing that might help you kind of remember that like x minus 4 squared, or like having something being squared gets you a double root, is because like say I could take the square root of both sides. You don't necessarily have to, but anytime we take the square root of a number, like even though it's 0, so this is kind of going to be like a little bit abstract, we get a positive or negative answer. So that's where the double root comes from. So if we square root both sides, the square root cancels out the squared. I'm left with x minus 4. And then the square root of 0 is still 0, but because we're square rooting, that's where we're getting that double root from. And then I can add the 4 to both sides and get x equals 4. So x equals 0 and x equals 4 are my zeros, or my solutions. And we just have to pay attention to the fact that x equals 4 is a double root, because that makes a big difference when we go to graph. And then for b, what is the degree? So this is already in standard form, meaning we're just looking at the highest power of x, so it's degree 3. Is the lead coefficient positive or negative? It's 5, so positive 5. So my lead coefficient is positive. For what is the y-intercept? So remember, the y-intercept is, so if it's on the y-axis, that's where x is 0. So if I were to find f of 0, that would give me my y-intercept. So if I were to plug in 0 for x, this would be 0, this would be 0, and so would this. So that means that my y-intercept is 0, 0. So it's 0, 0, because if I were to find f of 0, that would be 5 times 0 cubed minus 40 times 0 squared. Oops. And then plus 80 times 0. And all of this simplifies to 0. So then just one more time, anytime you want to find the y-intercept, just plug in 0 for x and you'll find the y-intercept. And then for e, if we want to sketch our graph, so we need to make sure that we include our x-intercepts, because those are for sure points that we know. So the x-intercepts we figured out were 4 and 0. And then we can plot a point at 0, we can plot a point at 4, and then we can start paying attention to what our end behavior is going to be. So we have a degree 3 polynomial, and then we also have a positive lead coefficient. So that means our end behavior is going to look something like this, where it finishes off going in different directions and it's increasing overall. So it's increasing from left to right. And then we also know our y-intercept. So typically, like with polynomials, if you know the y-intercept, that's like really the only scaling that you would need to put on the y-axis, and you'll see that on like a next example. And the big thing is just like scaling the x-axis so that you can get like the x-intercepts. So we have our x-intercepts are 2 points, and then we know the degree and the end behavior because of the positive lead coefficient. So from there, like if I look at my end behavior, as the graph goes left, it starts to go downward. So for my leftmost point or my leftmost x-intercept, I can finish off going downward. And then from the right, it finishes off going upward. But one thing that we have to keep in mind is that it's a double root at 4. So that means the function is going to bounce off 4. It's not going to cross through 4. So I know for my rightmost point, it's going to finish off going up. And then because I have a double root at 4, the graph isn't going to cross through 4. It's going to bounce off 4 and then come back up and cross through 0, 0. So 0, 0 happens to also be my y-intercept also, so I don't have to worry about including a different y-intercept, that's the only one. But we just have to pay attention to x-intercepts, the fact that this is a double root, so it doesn't cross through it, it just bounces off of it. And because it's a degree 3 and it's a positive lead coefficient, the right side is going to finish going up and the left side is going to finish going down. And then for number 4, it says find the zeros of the function f of x equals negative 2x to the 4th plus 16x squared minus 32, and then sketch the graph of the related function. We want to make sure we factor it completely, and then we need to consider degree, leading coefficient, and y-intercept. So if we want to find the zeros, that's essentially just solving it. So finding the zeros means we replace f of x with 0, and then equals negative 2x to the 4th plus 16x squared minus 32. And when we go to factor this, the first thing we want to check for is greatest common factor, and they're all divisible by 2, but because the first number is negative, I'm going to factor out a negative 2. So 0 equals, if I factor out a negative 2, and then I'm left with x to the 4th plus minus 8, if I factor out the negative 2, minus 8x squared, and then plus 16 for 32. And then now I have negative 2 times x to the 4th minus 8x squared plus 16. You could technically divide out the negative 2 if you want. It doesn't really make a difference in the end. But we can factor the x to the 4th minus 8x squared plus 16 further. So even though it's x to the 4th and x squared, it factors the same way as a quadratic would. So this coefficient is 1, so we're still just looking for factors of 16 that add up to negative 8, so negative 4 and negative 4. So 0 equals negative 2, and then times, it'd be x squared minus 4 and x squared minus 4 instead of like x minus 4 and x minus 4, because we're starting with x to the 4th. So this x to the 4th is going to get broken down into x squared and x squared. And then the factors that we figured out that multiply to 16 add up to negative 8 were negative 4 and negative 4. And you can write this as squared if you wanted to, but we are going to have to factor it further, so I don't know if that's necessarily helpful here. So x minus 4, or x squared minus 4 is now a difference of squares. So it's like x squared is obviously a perfect square, and then 4 I can think of as 2, or 2 squared. So they're both difference of squares, so it'd be 0 equals negative 2. And then this first x squared minus 4 factors into x plus 2 times x minus 2. That's our like a squared minus b squared factors into a plus b times a minus b. So both this x plus 2 and x minus 2 just came from this first x squared minus 4. This second x squared minus 4 also factors into x plus 2 times x minus 2. So we have 0 equals negative 2 times x plus 2 times x minus 2 times x plus 2 times x minus 2. So we could write that in like a more simplified way as negative 2 times x plus 2 squared times x minus 2 squared. And then we can kind of start to see that they're going to be double roots because it's the same factor occurring multiple times, or happening at least twice. So once we're ready, we can set each factor equal to 0 to solve for x. So x plus 2 equals 0, x minus 2 equals 0. You can write the squared and then square root both sides if you want, or you can just write the factor. I don't really have a preference. The big thing is just recognizing that it's a double root, and that's going to change the way your graph looks. So for x plus 2 equals 0, if I subtract 2 from both sides, I get x equals negative 2. And then for x minus 2, if I add 2 to both sides, I get x equals positive 2. So x equals negative 2 and positive 2, and they're both double roots. So now we're ready to sketch the graph. So I know I have solutions at negative 2 and positive 2. So those are my x-intercepts. It also says, or it says think about the degree, leading coefficient, and y-intercept also. So the degree is 4, and the lead coefficient is negative 2. So since our lead coefficient is negative 2 and our degree is even, our end behavior is going to look different than the other examples. It's going to both sides are going to finish going downward. So if it's an even degree, they both finish going in the same direction, and because it's a negative leading coefficient, the function will be increasing overall, so they're both going to finish downward. If this was a positive 2, it would just be both finishing upward. And then one other thing to keep in consideration is the y-intercept. So since this is in standard form, it's really easy to see the y-intercept. When something's in standard form, the y-intercept is just the constant. So remember, the y-intercept you can find by plugging in x equals 0. And if I were to plug in x equals 0 here, this would cancel out, this would cancel out, and I'd be just left with negative 32. And especially since this is a sketch, like I don't really expect you to go all the way down to 32. You'll just scale it accordingly and just make that one scaling or one tick mark on your y-axis negative 32. So you don't need to go all the way down. It does not need to be to scale. You just need to include that point there. So we have an x-intercept at negative 2. We have an x-intercept at positive 2. And then we have a y-intercept at negative 32. And then we know as we go to the left, our graph is going to finish down. So for my leftmost point, I can go down. I know that the graph is just going to bounce off of my double root. So since negative 2 is a double root, the graph is not going to cross through it. It's just going to bounce off of it. And then it'll cross through the y-intercept at some point. It'll come back up to my next solution at 2, at x equals 2, and it's going to bounce off at x equals 2 because it's also a double root, and it'll finish off going downward. So one more time, negative 2 is a double root, so it's going to bounce off negative 2. Positive 2 is a double root, so it'll bounce off positive 2, and then the end behavior based on the lead coefficient and the degree tells me that as the graph goes left, it's going to finish going down, and to the right, the graph is also going to finish down. And then it just needs to cross through the y-intercept of negative 32. And then for number 5, solve 2x to the 5th plus 24x equals 14x cubed. So in order for us to solve it, we first need to get it in standard form. So I'll have to subtract the 14x cubed over. So when I do that, I'll have 2x to the 5th minus 14x cubed plus 24x equals 0. And then from there I can pull out greatest common factor, which they're each divisible by 2, and I can pull an x out of all three terms. So I'm going to factor out a 2x. When I factor out the 2x, that'll leave me with x to the 4th. From the negative 14x cubed, that'll leave me with the negative 7x squared. And then for 24x, that'll leave me with 12. So because instead of a quadratic, I have like x to the 4th minus 7x squared, I know that my factors will break down into like x squared and x squared, but since this coefficient is 1, I'm just looking for factors of 12 that add up to negative 7, so that'd be negative 3. and negative 4. So this 2x will stay out in front. And then the x to the fourth will break down into x squared. And then minus 3 times x squared minus 4, my other factor, equals 0. And then from there I'm going to rewrite this up here because we have a little bit more factoring to do. So 2x times x squared minus 3 times x squared minus 4. And remember, you can always check to see if you factored it correctly by foiling it back to see if you get here. But you'll really only have problems like if it's not x squared and x, no matter what, like this will be an even number that you'll see at least in this class, and this number will be half of it, and that's how you're factoring these, just like you would factor a quadratic. It just cuts in half to x squared and x squared. So right now we have 2x times x squared minus 3 times x squared minus 4, and then x squared minus 4 is a difference of squares, so it factors into a plus b times a minus b. In this case, like a would be x and b would be 2, since 2 squared is 4. So 2x times this x squared minus 3 is just going to come down. And then x squared minus 4 factors into x plus 2 times x minus 2 equals 0. And then now this is factored completely, so I can set each factor equal to 0 and solve. So we'll set 2x equal to 0, x squared minus 3 equal to 0, x plus 2 equal to 0, and then x minus 2 equal to 0. So for 2x equals 0, if you divide both sides by 2, you get x equals 0. For x squared plus 3, if you add 3 to both sides, you'll get x squared equals 3. And then you have to square root both sides. So you get x equals positive or negative root 3. For x plus 2 equals 0, subtract 2 from both sides, get x equals negative 2. For x minus 2 equals 0, add 2 to both sides, get x equals positive 2. So we have solutions at x equals 0, x equals positive or negative 3, x equals negative 2, and x equals, positive or negative root 3, and then x equals negative 2 and x equals positive 2. And then number 6 says, find an equation of a polynomial that has zeros at x equals negative 3, x equals 1, and x equals 4. Think about working backwards. If you were solving an equation for the zeros and using the zero product property and got x equals negative 3, what must have been one of the factors? So it kind of helps. It may not be necessary, but sometimes it helps if you think like x minus k. And then whatever your k value is, like happens to be your solution. So if I were to get a solution of x equals 3, the factor that would have gotten me that solution would have had to be an x plus 3. Because when I solve, I set my factors equal to 0. And then here I would subtract 3 over to get x equals negative 3. So the factor that would get me x equals negative 3 as my solution would be x plus 3. The factor that would have gotten me x equals positive 1 as my solution would be x minus 1, because this would be equal to 0, and I would add the 1 over. And then for x equals positive 4, the factor that would have got me that would be x minus 4. So you kind of flip the signs if you want to think about that. You could think x minus k, like if we make this negative 3k, it'd be x minus negative 3, so the factor would be x plus 3. There's different ways to look at it. And then if I want to like write the polynomial function that has those zeros, I can just multiply all those factors together. So f of x equals my first factor, x plus 3, the next factor, x minus 1, and the next factor, x minus 4. Because if I were to find the zeros, like finding the zeros means I replace f of x with 0, and then I set each factor equal to 0. So like x plus 3 equals 0 would get me x equals negative 3. X minus 1 equals 0 would get me x equals positive 1. X minus 4 equals 0 would get me x equals positive 4. And then this doesn't necessarily say write it in standard form, but if you want to write it in standard form, if you're ever asked to, just in case, you just kind of need to multiply everything through. So this is factored form. So like f of x equals x plus 3 times x minus 1, and then times x minus 4 is factored form. So if it says factored form, you can leave it like that. If it says standard form, you need to multiply it through. So we'll just multiply the x plus 3 times x minus 1 first. So x, you're just foiling it. So x times x squared, x times x is x squared. X times negative 1 is negative x. 3 times x is 3x, so together that's 2x. And then 3 times negative 1 is negative 3 times x minus 4. And then x squared times x is x cubed. X squared times negative 4 is negative 4x squared. 2x times x is positive 2x squared. 2x times negative 4 is negative 8x. Negative 3 times x is negative 3x. And then negative 3 times negative 4 is positive 12. And then from there, you just need to combine like terms. So final answer would be f of x equals x cubed. And then negative 4x squared plus 2x squared would be negative 2x squared. Negative 8x and negative 3x would be negative 11x. And then bring down the plus 12. So once it's multiplied all through, that becomes standard form. And then for what degree polynomial did we get? I mean, we see it once it's in standard form, and I guess a factor form also if you just count the x's, but we got a degree 3 polynomial. And for 7, if we want to solve 7, x cubed minus 2x squared plus x minus 3 equals 0. So this time we have 4 different terms. So if we have 4 different terms, we want to use factor by grouping. So we'll split the left side of the equation in halves. So between x cubed and negative 3x squared, you can factor out an x squared. And that leaves you with x minus 3. And between x minus 3, there's not like a GCF there. So I can just factor out a 1. So plus 1 times x minus 3 equals 0. And then if I pull the x minus 3 out of both these terms, it leaves me with x minus 3. And then times x squared plus 1. And then from there, this is factored fully, so I can just set each factor equal to 0. So x minus 3 equals 0, and then x squared plus 1 equals 0. For x minus 3, you can add 3 over and get x equals positive 3. For x squared plus 1, you can subtract the 1 over, get x squared equals negative 1. And then if I square root both sides, I get x equals positive or negative I. So x equals 3 and x equals positive or negative I. And then for how many solutions we get, we ended up with 3 solutions. So the 3, the positive I, and the negative I. And then 1 was real and 2 were imaginary. So you may start to see there's been kind of a correlation between like how many solutions there are to the equation and how many or what the degree of is the equation. So like if we go back up even like in like just this page, this equation or number 4 was a 4th degree polynomial and we had 2 double roots. So if you count like a double root as 2 different solutions, we had 4 solutions. For number 5, we solved this and we were looking for how many solutions we had, or we're just finding the solutions. This was a degree 5, and there's 1, 2, 3, 4, 5 solutions. For 6, we wrote an equation that had 1, 2, 3 solutions, and it ended up being a degree 3. And then for 7, it was a degree 3, and we ended up with 1, 2, 3 solutions. For number 8, this one would be a really good one. Number 8 and number 9, this would be a good time to kind of pause it and try it on your own. So for 8, it says find the zeros of the function f of x equals x cubed plus x squared minus 6x, and then we want to sketch the graph. So anytime it says find the zeros, we're replacing f of x with 0. So 0 equals x cubed plus x squared minus 6x. And if I want to solve, I can factor it, but the first thing I have to do is check for greatest common factor. So I'm going to pull out a x, and then that leaves me with x squared plus x minus 6. And then because my coefficient of x squared is 1, I'm just looking for factors of negative 6 that add up to 1, since the coefficient of x is 1. So that would be 3 and negative 2. So 0 equals x, and then this factors into x plus 3 times x minus 2. And then I can set each factor equal to 0. So x equals 0, x plus 3 equals 0, and x minus 2 equals 0. For x plus 3 equals 0, subtract 3 over, get x equals negative 3. For x minus 2, add the 2 over, get x equals positive 2. So we have solutions or zeros or x-intercepts at x equals 0, negative 3, and positive 2. So that helps us sketch the graph. That's like the biggest thing that we need for the graph is those x-intercepts, those solutions. So we have an x-intercept or a 0 at 0, at negative 3, and at positive 2. And then our function is a degree 3, so it has an odd degree. It has a positive lead coefficient of 1, so that means my end behavior is going to finish off, it's going to be increasing overall, and it's going to finish off in different directions. So if we look at the end behavior as it goes right, the graph finishes going up. So from my rightmost point, I can go up. From my leftmost point, I can go down. And then none of these are double roots, so that means that it's going to cross, the function will cross through all of the x-intercepts. So it's going to cross through at negative 3, turn back around at some point, cross through at 0, turn back around at some point, cross through at 2. And then for 9, it says write a polynomial function f that has a leading coefficient of 1 and zeros at negative 1, 2, and 5. So if it has zeros at negative 1, 2, and 5, zeros are the same thing as solutions. So the factors that would have gotten me those solutions are x plus 1, because it would be like x plus 1 equals 0, and then subtract the 1 over to get x equals negative 1. For x equals 2, be x minus 2, and then for 5, it would be x minus 5. So same thing, you kind of think x minus k, and those k values end up being your solution. So if I want to write the function f, we'll start with f of x equals, and then I'm just going to multiply all 3 of my factors together. The lead coefficient of 1 just means that we don't have to worry about having like kind of an a value out in front like we did with when we're writing equations for quadratics. So I'm just going to take my 3 factors and multiply them together. So x plus 1 times x minus 2 times x minus 5. And then again, this is in factored form. If we want to get it in standard form, we just have to multiply through. So f of x equals, if I FOIL the first 2, x times x is x squared, x times negative 2 is negative 2x, and 1 times x is 1x, so this becomes minus x. 1 times negative 2 is negative 2, times x minus 5. And then if I multiply these two together, x times x is x cubed, x squared times negative 5 is negative 5x squared, and then negative x times x is negative x squared, so that's negative 6x squared together. And then negative x times negative 5 is positive 5x, negative 2 times x is negative 2x, so together that's positive 3x. And then negative 2 times negative 5 is positive 10. So if the problem or if the homework problem or whatever just says standard or factored form, you can leave it like this. If it says standard form, make sure that you multiply it all the way through. Just pay attention to what form it's asking for. And then the last little bit of notes that we're going to talk about is the fundamental theorem of algebra. So if you want to pause it, read it, feel free. But it says a polynomial of degree n with real or complex coefficients has exactly n roots or zeros, which may be real or complex. So remember, complex is just like it may have an I in it, or maybe it have an imaginary aspect to it. This also means that the polynomial has n linear factors, since for every root a, x minus a is a linear factor. For example, the polynomial p of x equals x to the fourth minus x cubed plus 20x minus 48 has exactly 4 roots or zeros because it's a degree 4 polynomial. And then it says, note that the total of n roots might include zeros that occur multiple times. For example, the third degree polynomial x squared minus 3x, x cubed minus 3x squared plus 4 has 3 roots, a root at -1 and a double root at 2. The 3 linear factors are x plus 1 times x minus 2 times x minus 2. Like I've said before, like sometimes theorems like are very wordy, but this one is like very straightforward once you get to like actually applying it. So for number 10, it says how many zeros does the function f of x equal x cubed minus 6x plus 21 have? If it's asking you how many zeros or solutions in general, you just have to look for the degree. So the degree tells you how many solutions there are, how many zeros there are. So since this is a third degree polynomial, it has 3 zeros. And then for 11, it says how many solutions does the equation x to the fourth minus 2x cubed plus 5x plus 12 have? Zeros and solutions are almost interchangeable. It's just like zeros for functions and solutions for equations. So we're going to look for the same thing. We're looking at the degree. So this is a degree 4. So there's going to be 4 solutions. And that's it. So the degree is going to indicate how many zeros, how many solutions there are to that equation or that function.